the bottom, we may want to group the pixels that are belonging to the foreground to the frog, or we want to group the pixels that are belonging to some segments or some regions on the frog. So the pixels that are belonging to the eye, or the pixels that are belonging to the arm or to the hand, and so on. Also, if we are looking on the right side, we are seeing a grayscale image, and yeah, we directly identify that we have three objects: the mug, the paper, and the headset. Okay, so we want to be able to segment to get the boundaries and to group together pixels that are belonging to these objects. Okay, so why is important the segmentation? Well, it is a basic operation that allows understanding of scenes. So if we are able to segment the people, we know the extent of each individual. We know also a bit more about the interaction between those individuals, and we can also have a better understanding of the background and what happens in that scene. We can also do some segmentation of medical imagery, and we are segmenting some internal organs. Okay, maybe the brain, maybe the parts of the brain, and then we can, based on these segmented regions, maybe the doctor could take some decisions, or we can provide some estimates on those segmented organs or regions. We can go for an industrial inspection. For example, we are segmenting some object, and based on the segmentation, we can assign some numbers, okay, that are related to the presence or absence of some defects. Okay, so we'll see a little bit about image segmentation through thresholding, then edge-based image segmentation, region-based image segmentation, and statistically pattern recognition-based image segmentation. So first thing, thresholding. So assuming that we have an image, for example here, this is a grayscale image, and if we are looking on the right, we have a histogram. So for all the intensities from 0 to 255, okay, we are in this histogram, we are getting an idea about the frequencies of those intensity values that are appearing in the image on the left. Okay, so by looking at this histogram, we are distinguishing two peaks in the histogram, and one is close to 0 and one is close to let's say 60 something, 70 value. So those two peaks here are likely to align with the object, the foreground, and the background. So the background in the end is black here. So this means the absence of color, absence of light. So it's close to 0. So close to 0 means background. And then the second peak here is corresponding to the foreground. Good. Now, if we are just applying a threshold and separate, let's say, in two groups, background and foreground, according to the threshold, and this threshold is 5, 25, 50, 70, and so on. Okay, we are just looking at the histogram, and just by looking at the histogram, already we know that our threshold is supposed to be somewhere here, around 50, 25 or 50. Okay, in order to have a good separation between the background and the foreground in a binary image. Okay, so if we are taking the threshold too small, then part of the pixels that are belonging to the background are marked as foreground. If the threshold is lying in between those two peaks in the histogram, then we are getting a rather good segmentation of the foreground and the background. However, if we are going further and we are setting a threshold that goes on the other side, on the higher part of the second peak, okay, larger values, then we are getting a lot of pixels that belong to the foreground that are ending up assigned to the background. Okay, so thresholding in the end assumes to binarize, okay, by imposing some threshold and end up with a segmentation of the foreground and the background. Not always this works easily, but is one way of doing segmentation, especially in controlled settings. Okay, so if the intensities of objects are known, everything is clear. We can just, instead of doing a simple thresholding, selection, and so on, we can just look directly at the intensities and define the object accordingly. So if we know that the objects are between 70 and 120, then obviously we'll just assign directly the pixels with those values to the foreground. Okay, so from a histogram point of view, we can take the minimum between 2 points. So for example, 2 peaks on the histogram, like here, we can just take something like here, and already we are getting some separation. Now, if we know the size of the object, then we can just move the threshold until the size of the object is matching, or the size of the foreground is matching what actually we know to be the size of the object. Okay. Another way is to maximize the sum of gradients at pixels with threshold intensity. So we are just looking for the threshold intensity pixels and check there the sum of the gradients. Another way is to go for low gradient magnitude areas, okay, and eventually, okay, another simple assumption is that everything that is on a flat region is supposed to belong to either foreground or background, right? So you cannot have two neighboring pixels of the same value that are belonging both to the same, okay, to a boundary between two areas. So by definition, if we have a boundary, then we have neighboring pixels of different values for the two segments that the boundary is defined for. Okay, so there are a number of ways of setting such a threshold for a given image and obtaining a binary. However, there is a more optimal way of picking a threshold, and this is the so-called Otsu criterion or method. So we want large areas of low variance. So if this is the case, then we want to minimize within group variance weighted by the group size. So in our case, if we are looking at the image, we want to have two groups, and here we have a depiction of the group 1 and group 2. Okay, so we have a group that is corresponding to the foreground, and we have another group that is corresponding to the background, and we want as much as possible the group 1 and the group 2, okay, to satisfy this relationship. So here we are just getting within group variance. So all the pixels here with white are belonging to group 1, so is the foreground. All the pixels with white here are belonging to the background, okay? And for these groups, we are keeping a number of pixels we have in the group and a variance of the grayscale values of that group. So obviously, we want to minimize the within group variance, so the variance in the values in the same group. And this regardless if it's the foreground or background. And if this is the case, then we are just doing this weighted expression here. We are weighing the variance with the number of pixels in one group and the other group. And as the groups are defined as those pixels above some threshold and below some threshold, okay, then we just want to minimize this expression with respect to the threshold. And we are getting an optimal value according to this expression of 35 in this case, and a clear, nice separation of the two segments here. Okay, so here are some other examples. We are getting some input image. We have our fixed threshold, and if we are just playing around, we may end up with something like this. If we are applying the Otsu threshold, that is at full image level, and we are just separating in two groups, we are getting this kind of result like here. However, we can also apply Otsu locally. So we are just getting a sub-region in the image, and we are computing Otsu in that local part, and end up with statistics to be locally minimizing this expression in local regions. So if we are doing this way, then we are seeing something that is closer to what will be our human annotation of a background and foreground for this input image. So here seems to be a little bit thicker in many parts, the text, while here we are just getting something that is adaptive locally. So we are still seeing here, between N and C, we are still seeing some black line and some other small details that are somehow better preserved here. Okay, so now not always we are getting the images in the clean conditions. We may have some noise, and even if we are landing up with a 35, like optimal Otsu threshold, okay, we'll see here quite a number of pixels that we consider to be noisy assignments to the background when actually they are on the foreground, on the object. So how can we cope with that? The so-called mathematical morphology. So our aim is to remove this kind of isolated islands or holes in the result of the segmentation. So given a binary image A, like here, and we have a binary structural element that is defined like this. So basically it's defined like a mask, let's say centered on some pixel, the middle one, and then we are just marking the other pixels that are taken into consideration by this binary structural element B. So we have the binary image, and we are defining some operations on this binary image. So our operations are shift invariant, nonlinear, based on pixel neighborhood defined by the structural elements, like here, and we are seeing the binary image as a set. Okay. The main two operations, morphological operations that we are defining are the dilation and the erosion. And how actually are defined, we see also the notation. So we have A, the binary image, and we are applying the binary structural element B. Okay, so we are applying, and then this application, here is a depiction of the application of this binary element. And we are applying in all the pixels in the image and replace the middle pixel, okay, with the result of this. So basically we are getting a simple operation. In the dilation case, we are doing an intersection between this structural element with the image, And if actually the structural element with the image is different than, okay, so has some pixels, okay, that belong to the foreground, okay, then if this is the case, we are just getting that pixels also to the foreground. Okay, in the case of erosion, is the opposite direction, is the opposite thing. So if actually there are pixels in the mask, okay, that are belonging to the or are belonging to the background, okay, then we are ending up removing those pixels. So the foreground pixels that are ending up in the middle of this pattern, and the pattern actually is intersecting, let's say, to the background, okay, then actually that pixel will just be removed from the foreground and left to the background. So here is just a simple example, just better understanding. We have this binary structural element, okay, and here we are just applying erosion and dilation. So if we are applying on this specific patch where this is the foreground and this is the background, the erosion says that, okay, we have our binary structural element applied to this. We have all those elements in the intersection. And in our, let's say, number of pixels that are affected by this operation, we are seeing elements that are belonging to the background. Then also the pixel in the middle will be set to belong to the background. So erosion means to turn foreground pixels to the background. And we are turning them when at least one of the surrounding pixels belongs to the background. And in the dilation case, with the same structural element, we are ending up with these points here. In the dilation case, we are saying that we are turning all the pixels in the background, okay, when the structural element is overlapping to some pixels in the foreground. So we are just doing this. Okay, so those are the mathematical notations of the erosion and dilation. And this is just a simple example. And what you need to note here, this is an example for this element. But as mentioned here, you can have whatever other structural elements. This element on the right can be quite often used. So, and now if we are applying for this input like here, the erosion is quite clear, the effect, more pixels are belonging to the background. The same for dilation, we are just ending up adding more pixels from the background. However, also in the process, we'll see that the effect of dilation is that we are removing the holes in the foreground, the holes in the object. So this is part of the positive effect that we were willing to have. Okay, so now if actually we are applying for some other image structure like this one, and we have our structuring element, this time is the cross. Okay, if we are applying this one and to obtain our erosion, we are seeing the surviving pixels. Everything else is left to the background. If we are applying dilation, then we are seeing the new added pixels from the background. Okay. Besides those two, erosion and dilation, we can define some other operations like opening, defined in this way, and closing, defined in this way. So the advantage of those is that for example, the erosion here is quite strong. Actually, all the pixels that are originally on the boundary will end up being assigned to the background. Okay, in order to not end up with this strong effect, one can use the so-called opening. So what means opening? Means that first is applying dilation and then applying erosion. And on the other side, for dilation, okay, in order to not get a lot of new pixels on the boundary, okay, we can do a so-called closing operation. This means that first we are doing dilation and then we are doing a erosion operation. And we are ending up with just smaller changes, especially on the boundary will be fewer changes. Okay, so those are morphological operations, and here is some result. And we are seeing the benefit of doing closing, for example, or opening. So for the opening, I remind you, is the equivalent to the erosion, only is mild. Okay, and we see here that mostly removes the islands that we had here. Okay, while the closing removes the holes, but we are not getting strong new pixels on the edges. Okay, so we can also do some binary enhancement as rank order operators. So what we are doing here, the new intensity based on rank to neighboring values, and we are just end up with an extension. Instead of working with binary, okay, we can go for gray level images, and then yeah, we can just adapt there and order the values and make this kind of notations and apply them. Anyway, so I'm not entering too much here. These are some basic morphological operations. Some people are still using them, were introduced 60 years ago, probably. Okay, it's good to know that they are there and can be applied if needed. So, typically it's used as a post-processing approach. And many times, actually, currently, instead of applying this kind of morphological operations, one can do directly a median filtering. Okay, instead of doing some dilation or opening or closing or whatever, you can just do a median filtering. And if you have just to remove holes, okay, then for some in a grayscale image and so on, you may end up with a similar effect as applying a dilation or a closing operation. Okay. Now, we can have also multiple objects in our image. And yeah, we can end up with a threshold. And this threshold will just separate between foreground and background, but will not tell us how many objects are there and how to separate the objects. So typically, if we are landing up to a binary image like here, then we may do a very simple thing. We have the binary. We are applying our post processing filtering or applying some morphological operator, end up with the two. We know that are two, but end up with the foreground without holes. Okay. And then we can just do an analysis of the connected components. So of the connected pixels in the foreground and connected pixels in the background. So what means to be connected means that actually the pixels, or between any two pixels that are belonging to a component, there is a path or a chain of neighbor relations between all the pixels along that path. Okay, and now in order to define a neighbor relation, okay, we can look at some typical ways. One is, okay, we are just considering that we have a pixel and we have a star, and this means that we are just considering to be neighbors, left, down, left, right, up, and down. So it's a 4 connectivity. Okay, we can have also a star that is going on diagonals and define some connectivity with the diagonal pixels, the neighboring pixels on the diagonal. Or we can have like a 8 connectivity. So we are just considering all the pixels surrounding the middle point, the pixel that we are focusing on. Okay. So depending on how we are defining the connectivity or the local neighborhood, neighboring relationship and so on, obviously is changing also the definition of the connected component, because it's based on the way the pixels are neighboring each other. Okay, so once we have the this definition, then in order to label the connected components, we can apply some simple algorithm. That means we are going line by line, a so-called TV scan or television scan. So pretty much we are just going from one line to another, or from one row to another, in left to right, left to right, left to right manner. Okay, so first we are doing the first line, and for each pixel, first we are just seeing what is the color, if its neighboring pixels, okay, if has no neighboring pixels that are marked, okay, then we are just marking with green, because already we processed that pixel, and everything else, all the other pixels are blue, and the current pixel just be marked with red. Okay, so given this configuration like is here, so we processed the pixels up to this the current line, and the pixels before ending up to the pixel red that is marked here. Okay, then we are just looking in the back and see all the pixels of that already were processed. Okay, and if no label is found, we start a new label. We just add a number. Okay, if we have a label, okay, and is a label that actually belongs to the immediate neighboring pixels that were already processed, then we are just copying to the current pixel. If we find more than one label, we are just marking the equivalence of the labels and assign to the current pixel the one of the labels, right? Okay, so at the end of going through all those pixels, we are having a list of labels that are equivalent, and we have all the pixels with some labels. Okay, so these labels in the end are defining the connected components, and we know that each pixel will just belong to one single connected component. So we can just extract back the connected components. This is a single pass connected component labeling algorithm defined for an image. And here, for example, if we are just getting this input, we may end up with this labeling. So we are getting one connected component that is this background here. Another connected component is this blue, light blue here, and then we are getting this more blue greenish color. Okay, And we are seeing here also some small connected components that are just some probably noise located here. Good. So now we have seen that the connectivity or neighborhood connectivity okay, can be like a arbitrary decision, or yeah, can be motivated differently physically and so on. But anyway, depending on the connectivity that is assumed, we may also introduce some topology induced metrics or distances. So here are a couple of examples like the D4 and D8 distances. D4 is known for as a Manhattan, so it's just going for absolute distance between the coordinates. Okay, while the D8 is going for the maximum. Okay, between the X and Y or I and J distances. Okay, so now if we are looking for D4 and D8, we have so-called disks of equidistant regions. So back, if we are considering that we are getting a pixel in the middle, okay, and then we are just depicting, for example, for this corner pixels, okay, or we are just drawing the pixels that are at the equal distance from the middle, we may end up with this in the case of D4, because it's just a summation of the difference of the coordinates on the X and on Y, or on I and J, like here. So I and J, we may just consider that is P, so is the middle point, and Q is whatever other point that is defined by K and L coordinates. So if we are just looking at this summation here, then all the equidistant points will just be on this kind of diamond shaped figure. And if we are just defining a disk, we are just going from distance 0 to distance whatever, an arbitrary distance, and we are taking all those pixels that are at the same equal distance from the point. Okay, if we are applying this formula 8, then actually we are getting this kind of shape for the equidistant regions. Okay, for an Euclidean distance, so you just need to remind yourself what is the Euclidean distance. So we have square root from I minus a power 2 plus j minus l power of 2, and we are getting the square root of that. Then we are getting a circle. Okay, so if we have the normal images and so on, we are pretty much forced to work on a grid, and we have I and j some discrete indexes. Then if we are playing with the Euclidean, okay, this is not conform with some discrete any discrete neighborhood that we are working typically with an image. But yeah, we can just define some other forms that are closer to an Euclidean. Okay, so now distance calculation or distance transformation. So for example, if we are getting the image on the left, we may just say, let's compute for all the pixels on the foreground, okay, some distance to the nearest or the shortest distance, shortest path to the background. And we are ending up with this. This shortest distance to the background is supposed to be defined by the neighborhood relationship that we define here. So if actually is a 4-star connectivity or is a 8-star connectivity, but anyway, and we are ending up with something like this that says, okay, those pixels that are in the middle are farther away from the boundary of the object and from the background. So this is a distance map of the pixels towards the background. So we can even define an Euclidean distance map, and yeah, it's just a matter of writing down some simple estimates whenever is necessary to compute such distances efficiently. Okay, so now we have seen about the thresholding as a image segmentation method. So the advantages are serious bandwidth reduction. We are just going from a grayscale image to a binary, or whatever is the number of objects in the foreground and background. Then we have a simplification for further processing, and typically can be done in real time. However, typically, generally, in most of the real conditions, outdoor real-world conditions, it won't work with sufficient accuracy, so won't provide satisfying segmentation. And is a pixel by pixel decision. Typically is ignoring the neighboring pixels and doesn't use the structural information. So we have some limitations. Here is one of the limitations. So assuming that we have some medical image with the organs, and yeah, in each pixel we are just getting some sort of score. Okay, then if we are applying thresholds, we are entering in this kind of problem. So we have many organs, okay, that are sharing some range of values. So then if we are just doing a simple segmentation, okay, between this group of organs and this group of organs, then everything seems to be fine in separating those two groups. But otherwise, we don't have any threshold, let's say, for this medical image that will not cut and place together, okay, more than one organ in the same foreground or background. So the idea of segmentation is to be able to isolate some segment that in the end is matching the target object or target foreground object or whatever. If we are not able to do it, yeah, then this is a problem with the threshold method for segmentation of images. So we have a strong overlap in intensity ranges, thus limited separability on the histogram. So if we are just looking here also on the histogram. Okay, so this was thresholding. Now we are looking at the edge-based. And yeah, if looking at pixel by pixel is not enough, then we should add some geometry or some extra knowledge to the segmentation. And one way of doing is to look at the edges. So typically the boundaries of the objects are made from edges. Okay, so if we are looking at the image on the left and we are applying O2 criteria and a single threshold, we are ending up with this separation between foreground and background. And clearly this is not a good segmentation. The biggest part of the foreground pixels are just assigned wrongfully. Okay, so we just see many pixels that are in the other group, so we don't have a nice segmentation of the foreground or of the background. However, if we are applying some edge detection, so we are just identifying pixels that are on the boundary, okay, and we can even extract some segments or like this with a Kenny edge detection. This is a standard operator for edge detection. We can see that the edges are typically found on the foreground image here, on the foreground segment or object. And moreover, there are some strong edges that are separating the object from the background. So having this knowledge, then obviously we want to link the edges and to, in this way, separate one object from the background. So we have a number of edge linking techniques. And here we are focusing mainly on a half transform for predefined shapes. So if we know the shape, how it looks like, then we can parameterize and look for that kind of parameterized shape and try to fit to the evidence, to the edges we are finding, or points we are finding. Then we have elastically deformable contour models. Some examples are the snakes. And those are typically applied for some generic shape priors. So this means that we don't know a fixed shape, okay? We don't have a parameterized shape. We just have something that can be almost anything or some generic definition, a large space. Okay, and we have quite a number of other methods that are a combination between some grouping and whatever other user input. Okay, so let's focus on a half transform, and first a little bit about the principle. So assuming that we know the shape is a fixed shape, like the ones from the bottom, okay, and we have some image. Instead of testing every possible position and orientation of that shape in the image space, okay, we are doing something else. We are visiting all the pixels, and for each pixel, we are trying to vote for some parameters of the shape that it may belong to. So for this, the half transform is strongly relying on the parametrics, on the parameters of the shape. And if we have these parameters of the shape, we know the number of such parameters. We can define some spaces of such parameters. And then when we are moving from one pixel to another, we are just casting some votes in that space of parameters. And then we are just looking at the amount of votes in that space of parameters and pick up the peaks in the space of parameters as being the most likely occurrence of the target shape. Okay, so the simplest example of half transform and simple shape model is the straight line. So here it's just a segment, but you can just imagine a straight line. What means the edge points then will vote for the presence of a line model. And yeah, obviously we can have some other generalizations to other shapes of the algorithm. But yeah, let's focus on the straight lines and how actually the half transform is working. So given points that belong to a line, what is the line? Okay. So we have some evidence, we have a number of points, and we just want to know where is and what is the line like. So another question is how many lines are there based on the points we have. and which points belongs to which lines. Okay, so assuming that we have this input image and we have some edge detection, or that is casting some edge points in the figure, then we just want to figure out how many lines we have there, where are the lines, and the pixels belongs to which line. Okay, the half transform is a voting technique that can be used to answer all these questions. The main idea is we are just going through all the voting pixels. So for example, edge pixels. And from each edge pixel, we are voting and keep recording the votes for each possible line that could cross that edge pixel. So edge point line. Okay. And then after recording the votes, we are just looking for those lines that are getting most of the votes, or a significant large number of votes, and then we are just looking back at those that pixels that casted those votes and identifying the image and project the lines in the image. So here is some example, and already you can just notice that depending on whatever is the threshold or the amount of lines that we want to extract, we may end up that quite a number of lines are missing. So for example, here is an edge that is missing. Okay, so probably if we are lowering the number of votes necessary for picking up a line, we can just get here multiple lines, and most of the edges will just have a supporting line. Okay, so this is the half transform, the general idea of straight lines. Let's see how exactly it is implemented. So we write the equation of a straight line as follows. Okay, we have a y equal with ax plus b. So x and y are supposed to be the coordinates of some pixel or point along the line, and the a and b are the parameters of the line. We have the slope and we have some, let's say, shift. Okay, then what we are doing, we are just fixing a point. If we are fixing a point in the line, we have x and y, okay, then all the lines that are going through that point, we can see them in this parametric form. So for a given point, x and y, all the pairs b and a that are related in this formulation, okay, will define lines that are going through this point, x and y. So this, in the end, is giving us a parameterization. So we have the parameterization of the shape, the straight line, like here. And here we have a relationship between the parameters with respect to the pixel coordinates, or the edge point that in the end will cast votes. Okay, so the half transform will do this. We'll just inspect all the x and y points of interest. So those can be the edge points, or it can be all the points in the image. But anyway, it's better to be some pre-processing and pick exactly the points that are likely to lie on the line. And for each x and y point, edge point, we draw the parametric line in a A-B parametric space. So we have A and B, the parameters that could define the lines, and here is just a simple visualization. We have x and y, the image space, and we have the A and B, the parametric space. If we are getting 3 edge points, A, B, and C in the image, then by using this simple equation, we can just cast lines in the parametric space that are going through this point, point A, and then we are ending up with this line. Okay, from point B, and we are ending up with that line, and point C, this line. So what is interesting here? So we are going from some points in the image, and then we are drawing some lines in the parameter space, okay, for all the potential tuples or doubles of such parameters A and B that may define a line that is going through that point. Okay. And if we are doing this for all the points, then we'll just see that these lines are supposed to intersect, okay, are likely to intersect. And then actually we can see some grouping that agrees for some parameter set, A and B. So for example, here we have A, B, and C, and all of them are agreeing for some parameters A and B, okay, in the parameter space. So this means that for that pair of A and B, we have 3 edge points, okay, that are voting for and are lying on that line. Okay, so a point in the image becomes a line in the parameter space, and a line in the image will just be defined by a single point in the parameter space. So a line in the image is actually defined by an A and B pair. A and B pair is just one point in the parameter space. So a point in the image is just an X and Y coordinate. It will just become a line in the parameter space, because along that line we are just getting different definitions of straight lines in the original XY coordinates for straight lines that are crossing that point. Okay, so now if we are going to the implementation, what we need to do? We have the parameter space, and unfortunately A and B are supposed to be continuous values, real values. Okay, so we cannot really draw these lines infinitely from minus to plus infinite and whatever. We cannot keep in the memory the whole space of parameters like is here, because A can be whatever and B can be whatever. So we need a discretization of this space. So we are ending up with a grid and definition of some cells. Okay, and this discretized parameter, we just call it accumulator. And then whenever we are drawing, basically we are just trying to see the intersection of the line that we are willing to draw in the parameter space with the discretized parameter space, and see how many such cells are intersected. And in each such cell, we are just incrementing the number of points that are voting for the presence of a line in that cell. Okay, so in this way, we are just getting a accumulator where that has a finite number of cells. Okay, these cells are counting the presence of some lines that are crossing those cells. Okay, and after we are doing this counting, we are just looking for the peaks in the accumulator space. So for example, here all those 3 points are defining lines, and the only for example, here, if you just look at this exact implementation, we see that in the accumulator, we have this cell and this cell where we are getting 3 lines crossing those 2 cells, right? And our peak in the accumulator space will be found here, and most of the space will be 0 votes. And in some other places, like here, or for example here, will be 2 votes. Here is also at least 2 votes. But anyway, the peak is found here and aligns well with the evidence that we have 3 points that are agreeing on the presence of a line that crosses all of them. Okay, now we have a big issue with this space, and already I mentioned that actually is not bounded. So, and moreover is actually undefined for vertical lines. So what means a vertical line? If we are looking at the definition and so on, it's difficult to cope with some vertical line where we are just getting a slope that is close to vertical, like here. So because yeah, the definition doesn't hold and we cannot draw a line. Okay, and then we have an unbounded parameter space. So A and B are not constrained, we're limited. Okay, the solution to this is the so-called polar representation. And the polar representation is like found here. So we have a transformation x, y, okay, and we have a theta and rho. So we have a new space that is represented by the theta and the rho, okay, and we have a relationship between this theta and rho based on x and y. So if we are looking back, we have a x and y. Rho is a distance from the centrum, and theta is representing an angle. So basically, a distance from the reference point is a perpendicular distance from the origin to a line, okay? So this is the line. We are extracting the rho, that is a distance to the reference, and we are getting an angle that is the angle the perpendicular is making with the x-axis. So if we are looking back, we are just having a x and y. We have a line depiction, and we have this encoding that we have a rho and a theta. Rho represents a distance from the reference to that line, and a theta that is an angle. So now each point, x and y, will add a sinusoidal in the theta rho parameter space. So now instead of having A and B parameter space, we have theta and rho parameter space. Theta, we know that is bounded, it's angular, is an angle, okay. And rho also can be bounded as a physical meaning if actually the distance goes beyond the size of the image, okay, and actually is not of interest because it's not in the image. Okay, so we are ending up with a new accumulator like that is defined by theta and rho space. We are drawing some sinusoids, okay, that are coming from this relationship between rho and theta, okay, and the x and y points. And these sinusoids are in the end casting votes for the lines that might cross x and y point. Okay, so if we are looking at those two examples, we have a square and a circle for all the points on the boundary. We are casting votes. This means we are drawing some sinusoids that are representing accurately the potential lines to cross in those points in this parameterized representation. And then we are just looking for peaks, and here we are getting 4 peaks, and those 4 peaks are corresponding to the 4 straight edges of the square and the supporting lines for them. However, if we have a circle, then we don't have strong evidence, strong supporting edge points, okay, to lead to a clear peak for a straight line. And this is the reality. In the end, is a circle. It's not containing some straight segments that could be seen as lying on a straight line. Okay, so this is just a visualization with normalization between 0 and 1, and we are just looking for some peaks. Okay, now we can see that if we are combining an image, so the same circle and square, and we are looking at the accumulator space, this is like an interesting thing. We can still find the 4 peaks of the edge straight lines, of the square straight lines, okay, and yeah, are quite clearly distinguishable, as well as we are just seeing that the circle is introducing these votes, okay, and still are not getting sufficient other support from the other pixels on the square to cast some other peaks that are relevant in this accumulator space. So from here, we can just infer that actually we can detect multiple objects, multiple edges at the same time in an accumulator space. So this is one advantage with the half transform. We are processing all the edge points, casting votes, and then we can just look in the accumulator space for the peaks, and we can extract multiple solutions at the same time. Okay, so now if we are looking for this image on the right, and we are looking at the casted votes on the left, I will just ask you what is very likely to be the line that generated the maximum peak in this accumulator space. So is anyone willing to tell me? Okay, so I'll make it easy. I will not move to the next slide until somebody is just telling me which out of those 4 lines, A, B, C, and D, is very likely to be supported by this peak here. Okay, anyone?
I think that B, but I don't have a strong argument for it.
Okay, so back to the definition of the accumulator, right? So in the end, in the accumulator, we are just counting the number of votes, and then those votes are coming from edge points, right? So if this is the case, then the maximum peak will be exactly that cell in the accumulator that is supported by the largest number of votes, therefore by the largest number of points that are agreeing for that line. So if we are looking back to the image, and you said B is aligning with this edge, right? We said already that for a straight line detection and so on, we are working with edge points. So B is on the edge of the object, okay, that has the highest number of pixels. So the highest number of points that could cast votes in the accumulator. So it's very likely that actually the maximum peak will be also provided by the largest number of edge points that are agreeing on the same edge, on the same straight line. So B is the correct answer here. That is very likely to have casted the highest or the maximum peak in the left image. Okay, so thank you. I'm just trying to figure out if actually you are following and how much. Okay, so now if we are just looking for the book, is a more complex case scenario. And we said from the beginning that, okay, if we are applying Otsu is not working. And we know that actually the book has some clear boundaries. And we have seen there that if we are applying some K-NI edge detector, we can just identify some edge points. And these edge points are clearly showing us some boundaries for the book. Now, if we are just getting these edge points from the K-NI edge detector, and we are casting votes in a half accumulator like here, and then we are looking for the peaks, we know that is a book we are expecting that are 4 lines. We are looking for the strongest 4 lines. Okay. And then we are just extracting for those 4 lines. Okay. Some straight lines. Okay. That are corresponding to these 4 peaks here. Okay. And then we are just projecting back in the image space. So this is a simple example where we can detect the book by casting votes for the straight lines and then projecting back and looking at the extreme points from the edge, okay, that supported that presence of the straight line, and we are just showing the straight lines that are likely to mark the boundaries of the book. Okay, so practical tips. We need to minimize the irrelevant voting points. So it makes no sense to vote without those points here. Okay. We need to choose a good discretization grid. So if we are looking back here, already I was pointing out that if we are looking in this accumulator, for example, actually we are getting 2 cells that are counting a maximum number of votes, 3 and 3. If actually this parameter space will have been much smaller, okay, the size of each cell and so on will have been much smaller and so on, then we can be more accurate, because also the cells themselves, okay, are in the end some range on the parameters of the parameters. So we just need a second estimation of the exact value of the parameters for those casted votes in each cell. So it's important to have a good discretization grid, okay, and the size of the cell, such that do not end up with a very large accumulator, number of cells, okay, but also do not end up with very, let's say, inaccurate or relaxed set of parameters that we are voting for. Okay, so then the vote for neighbors. So for example, in the voting phase, we can cast the vote for the current cell, but we can also cast some votes in the neighboring cells, assuming that there is some uncertainty. Okay, if actually the straight line there is really at that position or is slightly affected by some noise. Okay, so then actually we can just cast votes also in the neighboring cells and ends up with some smoothing in the accumulator. And we can weight the votes. So for example, by the how strong is the edge, and how strong is the edge is a matter of, for example, intensity, gradient, magnitude. And we can just use everything we know, like the direction of the edges, in order to cast votes. Okay, so this is a interesting technique. Half transform is good to know the basics, because yeah, you may see it again and again, and is quite often used. So the pro for the half transform, all the points are processed independently. We can cope with occlusions and gaps. Some robustness to noise, because noise points are unlikely to affect the voting outcome if are just randomly present. Okay, it can detect multiple instances of a shape model in a single pass, like we have seen here. We can detect all the 4 straight lines that are defining a square in the same accumulator after doing a single pass on the edges and their votes. However, we can have some shortcomings, like the time complexity goes exponential in number of model parameters. We have some ambiguities with the peaks, Okay, especially if the shapes are close by and then different. Some pixels are just waiting for both shapes and so on, and we are just ending up with some pixels that are just generated wrongfully, okay, as a summation of some edges that are present on two instances of the same shape. Okay, and yeah, discretization can be quite tricky. How to determine the grid size, and finding a good peak detection or a good estimate of the peak is non-trivial in many cases. Okay, so that was the half transform. Now we are looking at the edges and boundaries. So we have example on the left, and here the raw edge output is not so bad if we are applying like a Kenny edge detector. However, if we are looking at the dog image, and if we are just looking at different thresholds, okay, for the edge detector, we clearly not get like a very nice alignment between the edges and the boundaries of the object. So quite often the boundaries of interest are fragmented and we have a set of cluttered edges. So what is the solution in this case? We just need to rely on some other models, okay, that are trying to make some sense from the edges, edge points, okay, and to fit some contours. So here we are speaking about the active contour models. For the snakes, already we see that it has 35 years and since the introduction of snakes. And what are here the main ideas? So we are assuming that the initial contour near some desired object is provided. So we are getting an initial contour, for example, initialized like a circle around some desired object, some region in the image. And then the goal is to evolve this contour, to push this contour towards the best fit to the object boundary. Okay, so the intuition is as follows. We can consider that we have like an elastic rubber band wrapping around structures to cover or fill in missing parts. So here we are just showing if we are getting some elastic and we are looking at our fingers and so on, we get some evidence, the points that our fingers are touching the band. Okay. However, we don't. We still have some missing parts, but we know that there is supposed to be an object there. Then we are just trying to stretch or to adapt the elastic such that to get this evidence into account, and hopefully this will be also the best fitted curve to contain the object. So here is some other depiction. We can have these black parts that are, for example, belonging are found there, and we have the strong edges on the sides of those. And then if we are just initializing some active shape, some circle or some band outside, then this can be evolved such that to get aligned to the exterior part of these black regions. Okay, if actually is initializing internally, then we need to evolve this band until the maximum and align to the inner part of the black part. Yes? I think that somebody has the sound on. So do you have a question? Okay, I think it's Vasile. Okay, if you don't have, I'm just setting the mode. Okay, so back to the idea, we have an initial configuration and some edges. And then we are just trying to evolve. We are showing here some intermediate case of evolving this contour until to converging to some final position. Okay, how to adjust or iteratively refine an elastic band for a particular purpose? First, we are defining an energy function that says how good any configuration is. Then we are just seeing and seeking for the next configuration that minimizes the energy. So we are just looking for some refined configuration that will just minimize the energy. Okay, so let's see a little bit of what means energy. Okay, given our snake, and the snake can be seen like here, a parametric shape, or a parameterization of a shape that has a number of points, and for each point we have some x, y coordinates, and we know the order of the points that is kept. Then we can just define something like this. We have an energy, a total energy, and this combines our internal and external energy. So the internal energy is encouraging the prior shape preferences like smoothness of the contour, elasticity, and eventually if we know some shape priors. The external energy is supposed to be image dependent and is encouraging the contour to align to the image contents, to the edges. Okay, a good fit between the current snake and the target shape in the image will yield a low energy. So this is, we are combining in the end some prior information to the image information, and we are getting a summation of these energies, and we want to minimize them. Okay, so yeah, if we are looking for a typical band or whatever, is a continuous, but however, we can just parameterize and consider that we are just getting something from 0 to 1 on the contour, and we can get all the points on that. This is like a continuous case parameterization. However, on our side, we are working with discrete points on the image. So we have a reduced number of points like n, and we can keep for each point some x and y coordinates. Okay, this is a visualization of what means external energy. So in the end, the external energy is relating to the image, to the evidence that we are finding. So measures how well the curve matches the image data and attracts the curve towards interesting image features like edges, lines, etc. So, for example, here we have the image on the left, okay, and here is just a visualization of magnitude of the gradient, for example, for this object. And yeah, for the magnitude of gradient and so on is just a visualization, and we are getting stronger peaks exactly for the edges of the object. So you can see a similarity like gravitational pull towards regions or whatever high contrast. So if we are just interpreting this like magnitude of the gradient, like it is here, then we are just saying the most interesting parts are those that are with the largest such magnitude of gradient. Okay, so if is to see interpretation, you can just think about gravitational pull. If you are dropping on top some contour, you just hope that that contour will just be pulled towards the highest magnitudes of the gradients. So then the external energy or the external energy, we are just looking at the gradients on x and y, Okay, the directional derivatives. So in the end, typically are computed like distance or difference between the pixel values. Okay, from one position and another. Okay, after applying some blur eventually, and the external energy at a point on the curve, for example, is computed like here, and the external energy, the summation of all those gradient magnitudes will just give this summation. The internal energy is related to the priors that we are imposing. We want the curve to be smooth, for example, and eventually, if we have some prior knowledge, we might know a little bit about the typical curvature along the curve or whatever, and we can just add some priors that are adjusting a little bit the energy formulation. Okay, so now for the internal energy, we can have like a deformation energy, and this deformation energy could contain like depicted here. So we can have this definition that are capturing like two terms, one that is penalizing some elasticity and the other one is penalizing or adding some stiffness. Okay, and here is just showing some different cases. If we are just setting these parameters differently, then we may favorize some curves that actually are not following exactly all this edge boundary on the object, and medium, and in a small case like here. So if the stiffness is quite strong, then we will not get a good aligned contour with the object evidence in the image. Okay, so those are some parameters that can be adjusted. However, this is our internal energy, and typically we are just combining the stiffness and the elasticity and some relationship, and we are just defining those like using this kind of formulas that are boiling down to some differences on the image at pixel level between neighboring pixels. Okay, so I won't enter in this because this is the kind of technique that is not much used nowadays. Okay, and in order to minimize such energies, there are quite a number of ways of doing that, like partial differential equations, greedy search, and dynamic programming. Okay, I will just skip this partial differential equations. And when it's coming to the greedy minimization, you can just look at this example. So assuming that we are starting with this active contour, and we are getting only 6 points, like depicted here, we just want to adjust these points in the direction of minimizing the energy. So if we are doing a greedy energy minimization, we can just go from point to point, and for each point locally, we are just taking the decision of moving that point such that to minimize the energy that we defined, the total energy that is combining the internal and external energies. So it's combining the prior information and the evidence, the edges in the image. Okay, so we can do in that way, and then we are moving to the next point, and okay, and we are taking this kind of local optimal decisions for the points, and that is just leading to a greedy algorithm. Not always is guaranteed to converge, and also not guaranteed to converge to the optimal, global optimal solution. Okay, another way is to use like a dynamic programming. This means to consider for each point space of possible positions, okay, and then to keep track of all the potential best solutions, okay, in each of the points. So if we are doing this way over some discrete set of points, or okay, we may end up having an optimal global solution that is just solving the this energy minimization problem. Okay, so we can have also some specific priors, like shape priors, and then we can just add some extra penalty that penalizes if the points are not following what is expected as a shape. So, and yeah, so I will just go faster through those. And to summarize, I'll just say, okay, so for especially in the cases where we don't have some prior or parametric shape of what we are looking for and so on, then this can be a useful tool. And yeah, we can just fit non-arbitrary, non-rigid arbitrary prior shapes. And we are getting some flexibility in energy function definition. However, the problems are coming from the local optimization. So typically we are relying on some local optimization, and we have all kinds of problems that are coming from the definition of the energy and everything else. So R is a large space of settings that needs to be done manually. Okay, so I won't enter in that, and let's take probably a break of 10 minutes, and then we'll resume and finalize this and enter in object recognition. If you have questions, just let me know. Okay. Okay. Okay, any question? If not, let's continue. So we have seen image segmentation based on thresholding, image segmentation based on ages. Now let's look at region-based segmentation. And for example, region growing is based on the segment homogeneity rather than the inhomogeneity around edges. So in the end, we are coming with the assumption that one segment typically represents a region where we are getting about the same values, the same flat area, okay, and we can use that information to grow regions, segmented regions. So we start with the detection of homogeneous regions as seeds in the image segmentation problem. So in our case, a flat region or homogeneous simply means that we have low intensity variance. So then these seeds or flat regions and so on are grown as long as some criterion is satisfied. However, this criterion or homogeneity criteria and so on is not a simple task or very straightforward. Okay, so for example, we have this image, and on this image, we are just growing some seeds of low intensity variance and keeping the intensity between two slowly floating thresholds and merging overlapping segments. Then we are ending up with something like this. So we are ending up with a segmentation like this, and often we are not getting a very nice segmentation. We are getting also some leakage risk. What means this is very likely to happen through low contrast edges. So we may end up having some gradient here, so not a strong edge, that in the end is just allowing two regions to be merged together, or two regions to grow together. Okay, and then we are ending up with this problem of leakage. So there are all kinds of ways of handling this region growing, and yeah, we can do a split and merge procedures. We are ending up with some regions and then try to split them and so on. And whatever other approaches. Okay, so that is like a region growing. Another type of algorithm is watershed algorithm, and this is aiming at so-called finding the catchment positions in the image intensity graphs. So what means this? We are starting with some local minima and the different implementations of water filling are available that are based on some region growing like the previous one. We are just expanding on some starting seeds in some directions, and we are ending up with some over segmentations if our criteria and so on is strongly enforce some homogeneity of the regions. Anyway, the thing is, both region growing and the watershed, okay, here are like techniques that were used like 20, 30, 40 years ago. Maybe nowadays are still used by some researchers, especially in some medical imaging. And here is like an example of what we could get if for this input, here is directly in Gaussian blurred image. So in the original image, we get something like this, and if it's blurred already, the segmentation might be quite significantly different if the original input is blurred, because by blurring we are just removing some strong edges that might separate different regions. And if that edge is removed, then we end up having larger segments. Okay, anyway, another, and this is more state of the art nowadays, is the statistical pattern-based image segmentation. And what happens typically in a statistical pattern recognition, we are having a general scheme. We are typically basing on features, some, let's say, measurable characteristics that are extracted in the image space, and typically is assuming some probabilistic and learned-based formulations. So given this pipeline, we have an object, we have some sensors, we are getting some measurements. Those measurements obviously will be images as a first observation. Then those images are supposed to be processed or pre-processed. We can do some feature extraction like we have seen before, looking for key points or whatever other interesting information in the image. And we can extract some features. And then based on those features, we can proceed with conducting some classification or some other modeling, learning based model. And we land with some interpretation or object class. So we have three alternatives, dominant alternatives, like unsupervised clustering, supervised generative modeling, and the supervised discriminative modeling. And obviously we can have some other formulations and so on. Anyway, so here we'll just provide a brief overview of what can be expected. So for example, we have application, we have this input image. We know that we have the object is the frog. We have a sensor, is the camera. We have some measurements. Those are the pixel intensities. Assuming that we have some features, the color, and we have some object classes, foreground and background. So now our task is to create some model and to be able to segment the frog from the background, or to land in some segmentation of the image that is meaningful. Another example is, okay, we have the human body, we have this image, the object, or the objects are actually the organs in the human body. We have some sensors, and those sensors are the computer tomography. Then we have some measurements, the X-ray, attenuation, the features, some unit, Hounsfield unit, and so on. And we have some object classes, the objects, the organs, and whatever is outside the organs. Okay, so in general, the features are essential and have major influence on the results. So the way we are defining the features will, in the end, lead to good solutions or poorly performing solutions. Okay, so here are a couple of the notations, basic notations. If we have a set of all possible classes, like denoted here, K such classes, we have M measurements and N features extracted for each measurement. Like denoted here, we can call the color feature is three-dimensional. We have the RGB, X-ray attenuation, one dimension, pixel location, 2 dimensions, whatever other combinations that we may have. Okay, Now, if we are looking at the unsupervised clustering, we want to distribute measurements to classes. So the goal is to get homogeneity within classes and reduce the variance over the features, and can take into account multiple features. And we are departing from what? We only know the features, and we don't have the information on the classes. So if we have the information on the classes, then we are in the case of unsupervised clustering or supervised segmentation. Okay, so if we don't have the information on the classes, then we need to find such information as the result of the unsupervised process. Okay, so the most known clustering technique that is running without supervision, so it's unsupervised clustering, is the so-called K-means algorithm, and I think that you'll have also in the laboratory. Maybe some of you already encountered this algorithm. It's very basic. So we are just assuming that we have K clusters, and for those K clusters or groups of pixels, in our case, we are defining some centers or means that are just the average over that class. Okay, and then what happens is that we are starting, for example, with a random selection of such cluster centers. Okay, well, a random partitioning of the pixels into those K clusters, and then we are repeating a number of iterations until we see no changes. So for all the measurements, we are assigning to nearest center the pixels, right? So for all the pixels, if it's just to stay close to the image and our scenario, we just go through all the pixels, and all the pixels, for each of the pixels, we'll just look at the nearest cluster center that we have at that point, and pick up the nearest such cluster center and take the label of that cluster. Okay, then we are looking at the new formed clusters, okay, and we are just updating the centrum or the average or the center of mass of that cluster by just averaging all the pixels that were assigned to that cluster. So if we are just repeating those two steps a number of times, we are ending up to some converged solution. This means that at some point we'll not do new or reassignments of the pixels to some other cluster from the one iteration to the other. Okay, so this is the basic K-means, and for example here we are just showing for the input image. If we are doing a K-means clustering, unsupervised clustering, and we are just assuming that we have two clusters, then one of the cluster will align probably with the foreground, like found here, and another one with the background. Then if we have three, we may end up with this result on the lower left side, and if we have four, we are getting even more refined, and already we are starting to see that the clusters will just align to the in such a way that the within variance between the pixels in each cluster will be small. So this K-means is extremely easy to implement. Is a very useful initial analysis for many problems. However, we need to determine the number of clusters. There are a number of proposed solutions for that. most of them are heuristics or based on some simple analysis. Then the initialization is critical. So for example, if we are looking here and the initialization would have been really wrong, so then we may end up that we never land with some seed in some area that will allow us to have some cluster present in the solution. So for example, I don't know, with k equal with 4, so if we are ending up with some seed that is wrongly placed, we may end up having a totally different set of clusters than what is shown in this solution. So this typically the initialization and getting stuck with a poor initialization is avoided by running with multiple initializations. So we are just repeating the k-means multiple times with different initializations. Those initializations could be randomly done, or we are just going for some more involving techniques. And yeah, we can also handle some multi-scale methods at the level of data and the space where we are working with. Okay, so we can have some generic probabilistic formulation and extract the features. We know that are different for each measurement, is a random, non-deterministic, and then we can just assign some joint probability distribution of features and classes, and then to look at the marginal distributions. The probability of each class occurrence is a priori probability of knowledge. We can extract it either from the full image or we have some priors. And then we have probability of observing a specific feature, and we can just determine that in the image eventually, or again, could be some priors. Then we can have conditional distributions. We can given class information, measurement likelihood, we given measurements as a class posteriori, and we are using some Bayes theorem and so on. Then we can just put all of those together, and here is for the human body example. If we are getting, for example, 4 classes, okay, and we are looking at the probability of having a bone, the probability that any pixel is a bone. We can have also probability for nervous tissue or muscle or air, and these probabilities could be provided like priors. And then we can also get some other specific estimates that are related exactly to the input image. And then we can have some probability of the pixel being born given its measurement of some value. Okay, so we can derive those things and try to use them in refining and improving the solutions. Segmentation of the images. Okay, so I won't enter in all the details that are here. Okay, you just need to know that you can elaborate the things in probabilistic terms, and then the whole problem is becoming like a minimization or maximization of some energy function or some function that is putting together the prior information and the known information from the image. Okay, so then we are having the supervised generative learning and the supervised discriminative learning for segmentation. So let's look a little bit at the supervised generative learning. So from individual pixels to combinations of pixels, the earlier probabilistic segmentation model considers each pixel independently and is quite similar to the simple thresholding because assumes independence between the pixels. And we are having some mathematical morphology for thresholding the results. Okay, anyway, we are obviously interested in the relationship between and in defining the graphical models that are taking the geometry into account. Okay, from individual pixels to combinations, we have a general formulation. We have classes for each pixel, like before. Let's assume that we have k classes or m classes, depends how is the notation. And we have some joint distribution for each for an individual pixel and how it's defined. Okay, and so on. I'm not entering in all the typical examples. Here is just a simple notion of the topology. So in the end, what means topology? So topos, place, and the logy, science or word speaking about. Okay, so topology is a matter of or related to the placement and the study of the relative placement. And here is just a reminder that, okay, everything started in Königsberg or Kaliningrad. Euler at some point wanted to solve some simple problems, like how to go through all the bridges at a single time or to minimize the distance. Somebody could cross all these bridges a single time. Okay, and yeah, then just formalized the bridges and the connectivity and assigned cost and everything, and ended up with a graph theory where we have a graph defined by some nodes, and the nodes were, for example, the bridges, and the connectivity were like direct paths between them. Okay, and yeah, then all kinds of other problems were solved using this formalization or this formal definition of well, real problems. Okay, so typically, or in our case, we are using images. We may consider that all the pixels on an image to form nodes in a graph, and then all these pixels or the nodes in the graph could be connected, and the connections could be some edges or links that are especially defined between neighboring pixels. So for that, we just need a neighboring structure, and typically we have a star neighboring structure. And then for each pixel, we just have a number of neighbors, and we can define some edges that are connecting the pixels. And then if we are just using the Markov random fields, we have some purpose there. We have some probabilistic interpretation, and we can define this one on top of a image grid like we have. Okay, and then it's just a matter of setting up the probabilities we are working with and some energies. Okay, I'm not entering in all the details here. You just need to know that, yes, there are Markov random fields, and were used and still used in some cases. And typically, we are just ending up to some optimization that is putting together some terms. And those terms are typically combining some priors or that are known about the, for example, if one pixel is more likely to if taken individually, is more likely to belong to one class or another. Okay, and then there are some other terms that are penalizing. But if two pixels are in direct connection and are belonging to different classes, okay, or if they are and yeah, sometimes we just need to take into consideration also which classes, because we can have some priors that are telling us exactly if two pixels are more likely to appear in different classes or not, given their real values and whatever are the classes and their priors. Okay, anyway, the thing is, at some point, you'll notice that if we are just solving a Markov random field on some general graph and so on, we have a NP or NP hard problem. So basically, we just want to find the optimal assignment of the pixels to different classes that is minimizing or maximizing some energy. And this is very difficult, especially if we are having high order relations or complicated topology. However, if we are working with our 2D image, so we have a grid and we have local relationships and so on, then we have some approximate image minimization methods that are working nicely and might involve something like graph cuts, max flow, and whatever other techniques that are typically linear or polynomial in the number of pixels. Okay, so this is something that is good to know. And for example, here are some examples. If actually we are just applying so-called relaxation or Gibbs sampling, starting from some noise, we are doing some initial segmentation, and then we are just trying to update the decisions in each pixel based on what we know from the previous iteration. Okay, and in the end is converging to some solution. Okay, so mathematically, these generative supervised models can be Carl-Song, can be flexible, can be generic, can be extended to various features. Is quite a number of research works, and there are links to Bayesian. Features are important. However, the optimization and the inference can be hard, and for high-dimensional features, the estimation of the distributions can be problematic. And we are dealing with latent variables and factors. And yeah, in some cases, we might not even have access to or can estimate distributions. Okay, another direction is the discriminative learning. So basically, we are just knowing some classes, okay, and we know some samples. We know the classes, and we know some measurements or observations that are for each class, okay, and we are just requiring a procedure that takes the features as input and predicts the segmentation label or class assignment. In terms of probabilities, is similar to directly modeling the posterior or its maximum. So we are just learning to map from examples some features to some classes. So we can do something like that, and then directly we can apply to the problem, to the input image, and take this kind of decisions locally in each pixel or for some pixel with some support, some extractive feature nearby. You can just remember about shift, surf, or some other feature descriptors that can be used and can be extracted in each pixel, for example. So in this example, we can have some training data, and this means that we are getting annotations, labels, from some whatever special people, like doctors and so on. And then based on this kind of training label data, we can just learn the predictor that is just mapping some feature to the label. And then we are just going to the test part and hope that the predictor, the label predictor, to work as well on the test images. So obtaining labels and so on can be very expensive, but is also having such labels is very valuable, and are quite a number of applications that can be applied to. Now, how to do this mapping, how to discriminatively learn between features based on training samples can be done in quite a number of ways. The basic methods could be like nearest neighbor or k-nearest neighbors. So as we discussed before, is just for a given class, we have a pool of features that are belonging to that class. Those features or feature descriptors were extracted from the training set of images, okay? And yeah, we know that for those feature descriptors, we have those labels. Now, if we have some new test image, we can just go directly and retrieve in the pool of training samples the nearest such descriptors, and then assign to the test descriptor the label that we found for the nearest neighbor in the training pool. Okay, we can go with some more complicated model and retrieve the k nearest neighbors, and then we can do whatever, either a voting mechanism or a combination mechanism to have some refined labels. Other ways could be like logistic regression. If we have two labels, background, foreground, or something like this, we can apply a logistic regression, and we are ending up with a very basic classification method. Then we have neural networks, and we'll see about neural networks hopefully in the next session of lectures. And we have decision trees, or and we can have also random forests. So basically, we are having a tree, and for some input, we are just trying to take a decision in the root. And based on whatever decision we are making, we are just choosing one of the branches and repeat the procedure in each of the nodes in such a decision tree. And at the leaf nodes, at the bottom nodes, we'll just have the label that is supposed to be for those samples that were ending up in those leaf nodes. Okay, so this decision tree is quite efficient, because in the end we have a number of levels in the decision tree that is quite small, and a number of decisions that are made there, and typically, depending on the implementation, it can be taken quite fast. And if we are not satisfied with the tree, or the trees are difficult to embed everything, we can rely on so-called random forest. This means just combination of multiple such trees, and then for a given input, we are just pushing that input to all the trees and end up with some leaf labels, and then it's just a matter of combining those labels, predictions from all the decision trees together to get a robust prediction. Anyway, so those are some typical discriminative learning approaches. We can we'll see anyway a little bit more about the neural networks and the what happens there in the next session of lectures. And yeah, typically For all those discriminative learning methods, we are just assuming that we have training data, and that training data is coming under the form of some input feature descriptor, for example, or sample, okay, and some output class label. And we just need to train a model that will fit the best this training data, okay. And yeah, we just need to pay attention to not end up in overfitting the training. So this means that typically the set of labeled samples is supposed to be divided into a training part, training proper part, a validation, and a test part. So the training proper part and the validation are meant for development and training of the model, okay, while the test part is supposed to be used only at test and to assess the performance of the model. So if we are just mixing up the train proper part and the test or the validation, then we are ending up in not being able to say something about the generalization capability of the model. And typically, we are just overfitting, doing maybe very well on the samples we trained from, and will not be able to reach comparable or good performance on new samples that we never seen before. Okay, so after we are getting the model, the mapper, then we are just getting some input image, okay, and we'll just predict the labels in each pixel. And this based on the same features that were also used during the training, and by using the mapping method that we learned before. So again, for the k-nearest neighbors, here is just a review of the technique. So for example, we have training examples, and here is a depiction, and we are just showing this depiction on a 2D projection. And we have two classes, blue and red. So this is what we have, the training samples. When it's coming to the test, basically we are extracting the same kind of features in the test image. Okay, and then we are just retrieving the nearest k samples or examples from the training pool. And then we just need to take the decision on the assignment to the label that either is the, for example, the more often occurring label in the k retrieved nearest samples, or we are just assigning to the nearest sample label from the training pool. Okay, so we can just end up with such assignment, and this is the nearest neighbor idea and k nearest neighbor idea. Okay, in order to apply this, we just need to define what means the distance or nearest. Okay, and yeah, we can use the Euclidean distance between feature descriptors. We can use some other formulations, like you name it, inner product, cosine, or some other defined definitions. If if the features are, I don't know, binary features and so on, we can just come with some other definitions and so on, or we can just have some whatever norm, Minkowski norm with whatever p index. Okay, so typically we need to define the mapping. What are the classes we are looking for, and we just need to see how we are using those k retrieve nearest neighbors in order to assign or to take a decision on the labels. So we can use majority voting, weighted majority voting. Majority voting means simply like this: we are just getting the most often occurring label. Weighted majority voting means that we are getting some votes that are weighted differently according to the class label, and we can also consider probabilities and uncertainties. Depends exactly on the definition that can relate to the density, the space, the distribution density, or whatever. Okay, so here is just a simple example. We have those points on the left, and then we are just showing here what will happen if we are applying k nearest neighbor with k equal with 1, with 5, or with 10. So if we are assigning the samples directly to the nearest, so we are just considering that the samples we have, okay, will just be in the same space, the same kind of features, and then we are just taking a decision based on what we know in the training tool. So if it's a nearest neighbor, we are getting this kind of boundaries and assignments between the two labels. If it's k nearest neighbors, then we can get some refinement, for example, based on a majority voting. And if we are getting 10, k equal 10, we are getting something like that. Okay, so we are seeing here that the more samples we are getting, the more likely that the boundaries to be smoother, because we'll go or will align closer to some statistics of the group and less of the statistics of each sample individually. Okay, so this is about k nearest neighbor. Is very simple, can be implemented, is flexible. However, are plenty of handcrafted set parameters and so on that decisions that we need to make. Okay, in order to make it run very nice. Okay, the other point was binary decision trees, for example. So here is just a depiction. We have internal nodes, we have leaf nodes, and we have some splits. Okay, and for each node we have a parent and a child, except for the root node and for the leaf nodes. Okay, so when we are taking the decision, yes, we are getting some sample, is going to the root of the tree, and then based on some criteria in each internal node, we are making some decision. That sample is more likely to go to the left or to the right, and based on this decision is just pushing to some other internal nodes and some other internal decisions until we are reaching some leaf nodes, and those leaf nodes in the end are carrying the label information and eventually some statistics. Okay, so this is the way a decision tree works. And then if we are just stacking together, we are getting multiple decision trees. And these decision trees are having hopefully different or some slightly different decisions or some slightly different ways of computing the decisions. Then assembling these kind of decisions, we are just benefiting from such an assembling because we are just averaging some information or putting together some more information from different such decision trees. Okay, so the key thing is each tree to be different than the others. If it's the same, then we have nothing. We just have a repetition of the same information. Okay, so one way of doing this is if actually the trees are just focusing on different sets of features. Okay, then by the definition, we'll just end up with different decision trees, and it's just a matter of combining their decisions. Okay, so when we are speaking about random forest, we are just ending up to the parameterization and the kind of test we are getting. Okay. So we have a forest of decisions. We can have a random forest if actually the structure and the trees will be randomly designed, and also the decisions could be randomly designed. Then pretty much we are just getting almost like a signature, and we are learning from data what is likely to be the leaf in leaf label in each of the three. Okay. So this is like a random process of defining trees. And then if we are just placing together multiple such random decision trees, okay, we are ending up with a random forest, and is also a powerful tool. Okay, what is important here to know is that are easy to implement, are very efficient, because typically the decisions are fast to compute, and the depth. So the depth of a tree just means in the end the longest path from a root to any of the leaves. Okay. Longest path means in the end the number of internal nodes that you are getting from the leaf to the root plus, okay, 1. Okay, so that is one way of defining the depth in a tree. And yeah, if the tree has a small depth and the decisions are easy to or fast to compute, we can just compute rapidly. And for example, Kinect, maybe most of you know about Microsoft Kinect and the applications they were using, especially for tracking hands and doing some segmentation of users, was using Kinect. Kinect was using a random forest in some early version. However, there are quite a number of parameters and parametric choices, and typically requires a large number of data, and the training can take quite a bit of time just to optimize over the whole set. Okay, so this was about image segmentation and a brief review of the techniques that you could see applied to the image segmentation. Now I will enter in the object recognition, and we'll continue next time what we are not able to do today. So we call it traditional object recognition because nowadays most of the recognition problems or high level understanding problems are handled with end-to-end models. And one of the most known end-to-end models are based on neural networks and the so-called deep learning. Can be also shallow learning. Is what is important is to be able to push gradients and to be able to learn mappings from inputs to the outputs. Okay. So in traditional object recognition is more concerned with techniques that were mainstream, let's say, 10 years ago. Okay. And some of the techniques are still valid nowadays, especially in combination with some end-to-end learning that is added on top. Okay, so let's depart from this. The current state of the art, we have neural networks and deep learning, and we'll discuss about that next week. Then for today, we'll be more on the traditional pre-deep learning approaches, some algorithms, and important to understand the field and the kind of applications and the importance for various other applications, the importance of the techniques. Okay, so we'll look first for a specific object recognition and then for object category recognition. When we are speaking about specific object recognition, we are speaking about identifying the same object in different images despite variations in pose and illumination. Okay, so the key thing here is same object. In our object category recognition scenario, basically we are looking to identify the object category despite variations in pose, illumination, and intra-class variation. So this means that we are interested in identifying objects that are not necessarily to be the same as the ones that we use in the training or to provide the definition of the class. Okay, and our aim is to label all the objects that are belonging to that class, even if we never seen them before. Okay, so this is a clear distinction between specific and object category recognition. Now for specific object recognition, we have we'll discuss about the definition, model-based, image-based, hybrid models, visual words, and indexing, and geometric constraints and ANSAC. Okay, so here, just to stabilize the concepts, we have specific objects versus category level objects. So on the left side, we have a specific object, and we are looking for that specific object in whatever test images. So our aim is to recognize the same object that we have a view or an image of, or a set of images of. Okay, while the category level objects are just assuming, okay, given some training images or some prior known training set or whatever labeled images, okay, that are containing, for example, cars, we need to be able to identify cars in any new test image, okay, and these cars are likely to be instances of the car category, but different than those that were used to define the class category at training. Okay, so already I'm speaking here about training and prior knowledge and so on. So most of the tasks in vision are just assuming we are getting some visual data, and we are just trying to label that visual data to infer some categorical label. Could be a class, or to regress to something that makes sense at a high level. Regress words, or regress some, let's say, activities. So people are moving in the scene or whatever, or some other interactions that might be, or whatever other understanding a human might have from the visual data. So basically, most of the vision algorithms that are handling a high-level understanding, there will be some inputs, the visual data, and the outputs will be some information that actually means just regressed or estimated labels or estimated high-level concepts. Okay, so basically here we have a specific object and we have an instance of an object class, and for the specific we are looking for the same instance, and when we are finding, we are fine with that. And for the category level, we are just looking for whatever other instances of the same category of objects. Here is some example. So, for example, if we are looking for some landmarks, whatever, Oxford building and so on, then we have a pool of images, and we just want to retrieve these objects from this large pool of test images. Okay, and here already is shown, for example, this and that are images that are containing the same landmark. So basically, we are in the case of specific object recognition. Like if we are looking for this building, here we are seeing the same building, okay, and we can just retrieve that one directly. Okay, so this is a case of specific object recognition. And the direct application is the so-called large-scale retrieval. And typically, yeah, you can see it also at Google image search and so on. Depends. There are quite a number of applications that will allow to retrieve some set of images, okay, that are containing the same or the provided landmark or same objects or similar objects. Okay, so if we are looking for the landmark, it's quite clear that we are just interested in getting images of the same. Why could be this useful? Well, maybe you have a single image. The internet has unlimited or a huge amount of images of the same landmark. And then if you are retrieving all of them, or a significant number of such images, you can just find the dense correspondences and create a 3D model of it. Or you can just retrieve some better images and get some priors to enhance or improve the quality of the image. Or just for the fun, or maybe you just want to see different viewpoints of the same building, or the most common viewpoint, or whatever interpretation. Or you are just a tourist, get a picture and you just want to be localized or some information about that building. So, for example, here is a mobile tourist guide. Okay, if you are just getting a picture, you can just recognize the landmark and whatever information is coming with that, including Google Maps or whatever position in the real coordinates. Okay, there are quite a number of challenges in order to do that. So, as we discussed a little bit before, we have challenges that are coming from the pose or the viewpoint changes, illumination, variation, occlusion, and clutter. So we need to cope with those and to still be able to robustly recognize the specific object we are looking at. Okay, so here is an example of illumination change, not only viewpoint and okay, so almost all, as mentioned before, an image in the end is just a matrix, okay, with some values that are corresponding to RGB, for example, or to grayscale. Okay, so in the end, we can work directly with the image pixel values, okay, and we have a representation of that image that actually is exactly the image itself. But this is difficult because we have a large number of pixels in the image. Then we are ending up with a large representation. And moreover, this is very specific at some scale and so on. So typically, people are trying to represent an image in a representation space, okay, by some vectors of values of equal size. Okay, and then if the dimensionality of this representation is reasonably low, then we are seeing the benefits of being able to compare or do operations on this kind of representations of the images. Okay, so already we discussed before about the feature descriptor, like SIFT. Okay, we can just imagine that we can assign a descriptor at the level of the full image. And what is important is the same kind of descriptor to be extracted also in the other images we are comparing with. So, yeah, the first thing is to determine the kind of numerical representation of the image or of the object we are looking at or we are working with. And typically we are just landing to some vectorial representation. We have a vector of some size, some dimensionality, okay, and that's it. We are working with that. So, okay, once upon a time, at some point in the 70 years ago, okay, people were just getting some local, some image, okay, trying to get some local geometric features like circles or squares and so on, and then cast some hypotheses about what could be like some other images, and then match those to some image database. So pretty much was like given some image, you just hypothesize, okay, different viewpoints of that image or different renderings or possibilities of that image, that object to occur. And then for all these hypotheses objects to try to match in some large image database. Okay, but this is a very tedious and slow process. And other ways were simply like this. We are just getting a model for the object, a 3D model, okay? And then we are just trying to fit that model to some input image. So we just need to regress, to optimize, and to end up with this prior 3D object and its 2D projection to match the contents of an image. For example, in 1965, okay, we were getting this kind of blocks world model. So we were having some blocks like we see here, and these blocks were in the end 3D models and trying to fit these blocks to some 2D image. And those were seen like primitives that in the end the world model or the world is supposed to be formed from a combination of such basic 3D structures. And if you would align or recognize all these basic structures, then basically you are getting a description of the input image from these basic blocks. Okay, for example, in 1985, also the 3D models and this kind of prior information was supposed to help in dealing with occlusions. So basically it took about 20 years to be able to handle occlusions for some constraint and simple images like here. Okay, so this was something that happened 60, 70 years ago. And more recently, we were having some invariant-based recognition of planar shapes. The crucial advantage of invariants is that they decouple object type and pose issues. So we have those two images on the left and on the right. Okay, so assuming that on the left we have a query image or the input image, and we have a large dataset of other images. Okay, we just want to match or to retrieve this swan that is on the right. Okay, how to do this? Well, we just need some invariant feature representation of the input image. Okay, that will allow us to get a good similarity score to the representation of this image in the same feature space. Okay. So typically, people were using for such images like signatures for the outlines, for the boundary of the figure. So, and these signatures, if actually were taken with quite a bit of attention, could have been invariant. You can just do the same kind of operations that we thought and discussed before, like getting some gradients, aligning to the dominant gradient, the original image, extracting the edges, then get the edge boundary, and along the edge boundary or the outline of the figure, we can just get a sampling of points, and those sampling of points in the end will lead us to some numerical representation of the figure. And then based on this numerical representation, we are just able to assign some scores, matching scores with some other images in a large database. And yeah, this kind of representation eventually is getting some invariance and can cope with some affine distortions and not only. Okay, so here is exactly what I mentioned. We have two images. In the end, if we are just aligning and we are just plotting like differences, if we are starting from the same point and we are getting relative differences, we may end up with the same description of the contour from the same starting point on the contour. Okay. There are some other works that are trying, for example, to work with projective invariance and to handle, for example, occlusions like here and other cases. And yeah. Now, so the model base in the end typically is assuming that we are using some local geometric features, and these local geometric features in the end are helping us to check the geometry of whatever happens in the target image. So we have seen about 3D models, we have seen something about the outline or the contour of the object. Then we have some appearance-based methods that can be used for recognition, and one of the basic ones is the so-called template matching. So given some template and some input image, we are just shifting the template over the image and compare the response of that shifted template to the image. So that response could be, like mentioned here, a sum of squared differences like we have seen before, or it could be normalized cross correlation, or whatever other distance that we are defining, or whatever other score function that we are defining. And then by checking the resulting scores, we can see some peaks, and eventually we are picking that peak with the that is there, okay, and is above some threshold, and take the decision that yes, the template containing hopefully the object is found at some location in the image. The problem is variation in the appearance because of changes in viewpoint and lighting. If actually we have this big problem, appearance changes, the variation, the viewpoint and lighting changes, and so on, then according to this basic template matching technique, then actually we need to know from the beginning, or to have multiple templates, okay, for all the potential or a set of potential changes in the appearance, changes that are provoked by viewpoint, lighting, or whatever other causes. And then all these templates needs to be checked for the test image and the results to be interpreted. So we see here that we are ending up in a highly infeasible approach to create templates and to match those is simply infeasible for most of the objects. Okay, but back to the PCA and working with the directions in the data that are carrying most of the information, then we can do what? We can just define, okay, we have the template. We can even define or generate multiple viewpoints and whatever other templates that are out there to represent this one. And then we can just run a PCA on top of all the templates that are representing the object we are looking for. Okay, and then we can just keep some directions with most of the information. This means that then we can just get the original template and project this one along the directions with the highest information through the eigenvectors completed with PCA, the principal components. And then we can just run or do this kind of template matching using a lower dimensional representations. Okay, then we have the PCA weights of the image that are our global image representation. Okay, so I'm just pointing out here that are ways of reducing the dimensionality or representing in a more compact way. And then, yes, we can afford to have a template matching technique, okay, that is working quite surprisingly well. And this is a work from '96 that was handling multiple viewpoints and viewing conditions, and then I was applying the PCA over all the images directly on the images. We keep the dominant principal component 120. Okay, and then a sequence of views for one object represent a manifold in the space of projections. Okay, so then for this input image, they were just looking at the nearest manifold pretty much in the projected space. This means in the projections obtained using PCA. Okay, so another way of doing is object pose manifold. So the images are put on a, for example, for a car, on a turntable, and the images from a fixed distance are taken under some elevation angle. So we have defined for some object azimuth, elevation, and distance to the camera. And we are defining with those parameters object pose. So the pose changes were limited to changing the azimuth angles, like here. And yeah, we have a discretization of these angles. And yeah, in the end, if we are getting a lot of images like this, we can just try to create like a manifold of the representations, okay, that are tied to the azimuth, the location. And then for a given input image, it's just a matter of finding in this manifold, okay, the closest or the closest points that are corresponding to registered points in the training. Okay, and if we are finding that, then obviously with the training is coming also the information about the pose. So the task here is pretty much if we are getting a image of a car, we just want to get the pose, the rotation in the end of the car. And this is one way of doing. We are just getting first recording cars at different angles on a turntable, create a space, a manifold space, and then for a query image, we are just trying to regress the angle or the pose information. Okay, so other examples are faces. So we are going into the direction of eigenfaces for a face representation. And here we are just seeing some standard deviations and the differences if we are getting an average model of the face and how this can be modified or sampled differently. Okay, the thing is almost like here was done using principal components. This is another prime example of principal components, the PCA, okay, where a huge set of faces. First, we are computing some eigenvectors, some statistics. In the end, we are just capturing the directions of the highest variation in the data. And based on those, we are able to create some models to capture the full information in the data. And yeah, we are just creating such models and then we use them. I'm not entering the details, but in the end, the models are quite robust. Okay, now there are some even more enhanced and better looking, better, more accurate models, but that is one of the basic. 3D reconstruction application. Okay, for example, if we have a 3D face, you may want to be able to fit a 3D model and extract from the image the texture for the face and estimate as well the pose of the face in the picture. Okay. Now, if it's just compare between the model-based and appearance-based techniques, okay, we have those, let's say, green and red let's say, features or characteristics. So for a pure model-based and for a pure appearance-based. So if the pure model-based is very compact, so we have the 3D geometry of the model, and can deal with clutter. If we have the 3D geometry, we have the geometry and so on, then we can just fit, and based on the geometry, we can cope with some clutter or some occlusions. On the pure appearance-based models, then we need to rely on multiple images, on a set of images, or something that combines a large number of images. So we are ending up with some large models. Okay, and not necessarily we can cope with clutter because each image individually or template individually, okay, doesn't have occlusion or reasoning with a clutter. So it doesn't have a model of the background. For the pure-based models, actually we don't need a model of the background because we are just relying on the geometry and the alignment to the edges and what appears in the image. Okay, so the pure model-based is very slow to analyze by synthesis because somehow we just need to cast hypotheses and to refine the casted hypothesis and yeah, it's almost like an optimization process. Okay, while the pure appearance based is more efficient, is or is not there, we are computing some distance or not, and make some decision. Also, the pure model based are difficult to produce because we need to have access to an object, the physical object, to create a 3D model. And in order to create that 3D model, we need either special equipment or a round table or a turntable, okay, and to be able to take multiple images and to record them and get a 3D model out of it. The pure appearance-based is easier to produce the models because we are just getting multiple images and eventually we are combining them or use them like they are. And the pure model-based is limited for limited object classes, while the pure appearance-based is for wide classes of objects. So, because in the appearance case, we don't spend or we don't require some controlled setting. We just require some views of those objects. Okay, so this is about the image-based and model-based and image-based specific object recognition. And in the next will be like hybrid models. But I think that we should stop here. Already the time is flying, and we'll continue next time with this. Now I will just invite you to not leave yet, because I'm just checking a little bit who is here, making the presence. Okay. So, do you have any questions related to the materials presented, discussed today? Okay, so if there are no questions, then have a nice remaining part of the weekend, and see you next time. Bye.
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 Nice day.
Okay, so probably they are not there. So
Yeah,
okay, happens.
99%.
Okay, so okay, Emilian is there, and now let's see.
Yeah, maybe he's waiting for the alarm.
Yeah. So let's wait one extra minute. No, he's not there. Okay, and I'm just kicking him out.
Yeah.
Okay. Okay, Catalin. I'm just kicking out.